Picture this. You're sitting at your desk. The glow of the monitor is reflecting in your eyes.
Yeah, probably at 2 in the morning.
Right, always at 2 in the morning. And you are staring down 3 massive industry-level engineering
And
problems.
these aren't just, hypothetical textbook exercises either.
No, not at all. These are the exact scenarios that make or break careers in the tech industry. So, problem number 1. You have 2 machine learning models. Let's call them Model A and Model B.
Okay.
Model A is the old reliable. It's currently running in production, and it's handling millions of requests per second. But Model B is your new creation.
Right. It's this complex neural network you've been tuning for weeks.
Exactly. And your initial offline tests, they show it might be slightly better at predicting user clicks. So the question is, do you push the button? Do you deploy Model B to your entire user base, risking your whole infrastructure and, frankly, potential revenue, just on a slight uptick in a local validation score?
It is a terrifying moment for any engineer, especially when the stakes involve actual computational cost and user experience. I mean, the numbers on your dashboard are compelling, but looking at a raw validation score never tells the whole story on its own.
Which brings us to problem number 2. You're looking at your data set, which is the lifeblood of your entire machine learning pipeline. And you've engineered a brand new feature. Let's say it's a dense vector representing the user's historical session duration.
A very heavy feature.
Super heavy. You think it captures user behavior perfectly, but including this new feature in your data set adds 50 milliseconds of latency to every single inference. Plus, it dramatically increases your cloud compute costs.
Yeah, those AWS bills add up fast.
They really do. So do you include it? Does it actually add predictive value, or is it just creating statistical noise that looks like a signal?
Feature selection is just a constant battle between signal and noise. You're constantly balancing computational overhead against theoretical accuracy. And without a rigorous, mathematically sound framework to evaluate the feature's true contribution, you're essentially gambling with company resources.
And that leads directly into problem number 3. You are part of a product team, you have version 1 of your recommendation algorithm, and you've just run limited user tests on version 2.
Like a canary release.
Right, a canary release to maybe just 5,000 users. The user tests seem to suggest version 2 is a massive hit. Engagement is way up. Do you launch version 2 globally based on that limited testing cohort?
That's the trap right there.
Exactly. How do you know for sure that those specific 5,000 people actually represent the millions of unique individuals who will eventually interact with your system? Every single machine learning engineer, data scientist, and AI practitioner faces these 3 decisions on a weekly basis. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry ready and apply your knowledge to real industry projects.
And being industry ready requires a significant shift in perspective. It means moving beyond just knowing the syntax of a Python library. I mean, anyone can import a regression model.
Yeah, pip install and you're done.
Exactly. The true value of a senior engineer lies in understanding the foundational underlying logic that dictates when to run that code, why you are running it, and most importantly, whether you can trust the output it generates.
Okay, let's unpack this. Because to solve those 3 massive problems, we need to confront the core dilemma of today's deep dive. I was going through the industry case studies we gathered for this discussion, looking at catastrophic deployment failures from major tech firms. And the common thread in almost all of them is something that just isn't talked about enough when you're first learning how to train a basic model.
It's the gap between theory and reality.
Right. In real-world machine learning projects, you never, ever see the entire population of data. You never see the whole picture. You only ever see a limited sample. A tiny, isolated slice of reality. So the master question we have to answer today is this: how can we possibly trust conclusions that are drawn from limited data?
That master question is the beating heart of everything we do in data science. Answering it requires us to build the foundation of statistical inference. Now, I know the word statistics might send a shiver down the spine of some developers.
Oh, absolutely.
You might be having flashbacks to memorizing complex, archaic equations on a chalkboard. But I want to assure you right now, today, we are conquering that fear entirely. We are mastering the concepts of inference, sampling, and hypothesis testing purely through intuition and mental models. You won't need a single complex equation to grasp this.
We are talking directly to you, the listener. We know you probably already understand some basic Python. You can probably clean a data set and train a standard classifier. Today is about bridging the gap between writing a script in a Jupyter notebook and confidently deploying an automated decision-making system to the real world. We need to start by breaking down the barrier between the data you have and the data you wish you had. Let's examine a classic quintessential industry case study, the A/B test.
The A/B test is the primary tool the tech industry uses to navigate uncertainty. It's the core methodology behind how platforms like Netflix optimize their streaming interfaces or how Google refines its search algorithms. It really is the empirical engine of the internet.
Let's set the scene using a scenario pulled from the research notes we're reviewing. You work for a massive global e-commerce platform. Your design team hypothesizes that changing the main buy button on the product page from blue to green will increase sales.
A classic design debate.
Right, but you can't just change it for everyone at once. That's way too risky. So you run an experiment, you show the new green button to 1,000 randomly selected users, you wait, you collect the telemetry data, and the results come in.
And what do they show?
Well, the conversion rate, the percentage of people who actually clicked the button and completed a purchase, it increases from a historical baseline of 10% with the blue button right up to 12% with the green button.
That is a massive jump at a global scale.
Huge. You see that 2% bump, and it translates to millions in projected revenue. Your immediate instinct is to celebrate and deploy. But here is the critical question the senior engineer asks. Did the green button actually cause that behavior change, making it truly superior, or did you just get incredibly lucky with the specific 1,000 people who happened to log on during your test?
That is the multi-million-dollar question, quite literally. And to answer it, we have to formally define the two distinct layers of reality at play here. First, we have the population.
And we don't mean citizens of a country here, right?
No, not at all. In statistics, the population is the entire theoretical universe of all possible data points for your specific problem space. In the context of your e-commerce case study, the population is every single person who currently uses your website, plus every single person who will ever use your website tomorrow, next month, and 5 years from now.
That concept is so vast, it's almost impossible to wrap your head around. You're including people who haven't even bought their first computer yet in this population.
It is entirely abstract. It's a theoretical construct because, in practical reality, you can never fully observe the population. You cannot test a UI element on users who haven't even discovered your platform yet. The population represents the infinite underlying truth of user behavior that you're attempting to uncover.
But we have to measure something.
Exactly. Because we cannot measure infinity, we are forced to rely on the second concept, the sample. The sample is simply the finite, observable portion of the population that you actually interact with. In this scenario, it's those exact 1,000 users whose sections were captured during the A/B test window.
So to put it in the plainest terms, the sample is a small, manageable subset of a massive, completely unobservable universe.
If we connect this to the bigger picture of machine learning architecture, grasping this mapping is non-negotiable. Your sample is your training data. When you query a database to pull 10 million rows to train a deep neural network, you are not downloading all the data in the universe. You are downloading a sample.
Even at 10 million rows?
Even at a billion rows. Your validation holdout set, that's a sample. The live experiment batches you route traffic to, samples. Every single machine learning model ever deployed in the history of computer science was trained on a sample. No algorithm has ever seen the entire population.
I was reading about the sheer scale of the data sets companies use now. Petabytes of information, trillions of parameters. It's so easy to fall into the trap of thinking, well, my data sets is so massive, it must be the population.
It's a very dangerous assumption.
Right. But even a data set with 1 billion rows is just a slightly larger keyhole. We are always looking through a keyhole, trying to guess the dimensions of the entire room. We are inherently building models based on incomplete information from the very first line of code.
The illusion of big data is dangerous. 1 billion rows of data collected under specific conditions is still a sample, and it carries all the vulnerabilities of a sample. That keyhole analogy highlights the next major roadblock in our pipeline. What happens if the keyhole you are peering through happens to be aimed at a highly unusual corner of the room? What if the view is distorted?
Which means we need to talk about sampling bias. Or, as I prefer to frame it when looking at failed model deployments, when the data straight up lies to you.
It happens more often than you'd think.
Oh, totally. Let's twist the e-commerce case study. We have our 1,000 users who saw the green button and yielded that incredible 12% conversion rate. But what if, entirely by accident, the routing algorithm for your A/B tests sent that green button primarily to users browsing on high-end desktop computers?
Okay, I see where this is going.
Right, maybe your test ran during work hours, capturing corporate users making enterprise purchases. But your actual overall user base, the true population that generates most of your traffic, is predominantly made up of teenagers using a mobile app on cellular networks.
This scenario is terrifyingly common in the industry. We refer to this as sampling bias. Stripped of the jargon, sampling bias simply means that the sample you collected fundamentally fails to represent the broader population you intend to serve. Your 1,000 desktop enterprise users do not accurately reflect your millions of mobile teenagers.
I want to clarify something here because this trips up a lot of developers. The raw data itself isn't technically wrong, is it? I mean, those 1,000 desktop users really did click the green button 12% of the time. The database logged the events correctly.
The logging is perfectly accurate. The sample is mathematically true to itself. The failure occurs in the extrapolation. The conclusion you draw becomes completely warped the moment you assume the rest of the unobserved universe behaves identically to that specific narrow group.
I was looking at the notes on survivorship bias, which is a fascinating flavor of this. The classic example is from World War II, looking at the planes that came back with bullet holes.
Ah, Abraham Wald.
Yes. The military wanted to put armor where the bullet holes were on the returning planes. But the statistician, Abraham Wald, pointed out they were only looking at the sample of planes that survived. The planes that got hit in the engines didn't make it back to be measured. If we map that to a machine learning problem, say, building a model to predict user churn, how does that manifest?
Survivorship bias in churn prediction is a perfect parallel. Imagine you are training an ML model to identify the characteristics of a loyal long-term user. You pull a massive data set of all the user activity from the past year, but your query only pulls data from users who currently have active accounts.
You're only looking at the survivors.
Exactly. You are analyzing the survivors. The users who downloaded the app, hated the interface, and uninstalled it after 3 minutes are completely missing from your sample.
Because they didn't stick around long enough to generate the deep engagement metrics your model is looking for.
Right. And if you train your algorithm on that data set, the model will assume that quick uninstalls just don't exist in reality. It learns a completely distorted physics of the user ecosystem. Sampling bias leads directly to what AI engineers call dataset imbalance. If your sample is biased, your neural network doesn't just ignore the bias, it mathematically encodes it. It optimizes for your blind spots.
And when you take that model, pack it into a container, and deploy it to the live production environment, when it finally collides with the true messy population, what happens?
It results in a catastrophic generalization failure. Generalization is the ultimate goal of machine learning. It's the ability of a model to perform well on new, unseen data. A generalization failure means your model looked like an absolute genius in the laboratory when tested on its biased training data, but it acts completely erratic and fails spectacularly when unleashed in the real world.
To give a highly technical example from the case studies, imagine a logistics company building a machine learning routing algorithm to optimize delivery truck paths. They train the model exclusively on historical GPS data collected from their fleet operating in dense urban environments like Manhattan and Chicago.
That's a very specific type of drive.
Very specific. The sample is massive, millions of data points. The model learns incredibly complex relationships about traffic like timing, one-way streets, and double-parked cars. Then the company deploys this model nationally, including to their rural routes in Montana.
The model will fail instantly. It was trained in a reality where the nearest valid road is always 50 feet away and average speeds never exceed 30 miles per hour. It cannot comprehend a reality involving 50-mile stretches of dirt road. That is a generalization failure rooted entirely in sampling bias. The urban data was mathematically flawless, but it did not represent the rural population.
This emphasizes such a vital, unshakable rule for anyone writing Python code to build these systems. An algorithm is only as trustworthy as the sample it learns from. You can utilize the most elegant, highly optimized transformer architecture, written by the most brilliant engineers, running on millions of dollars of GPU hardware, but if your sample is biased, your output is worse than useless. It is actively misleading.
It is the ultimate high-stakes manifestation of garbage in, garbage out. The architecture cannot save you from flawed data. Recognizing, auditing, and mitigating sampling bias before a single epoch of training begins is the hallmark of a senior ML engineer.
I'm looking at these deployment disaster notes. And it seems to me that even if we are incredibly careful, even if we build complex stratified sampling pipelines to ensure our 1,000 e-commerce users perfectly mirror the exact demographic and hardware breakdown of our global population, we still have that primary problem.
We still only have 1,000 people.
Exactly. Perfectly representative, yes, but still just a tiny fraction of the billions of global users. We still don't know if that 2% bump from the green button was just a random fluctuation. How do we mathematically prove it isn't luck without observing the whole universe?
To bridge that gap, we rely on what is arguably the most beautiful, powerful, and fundamental phenomenon in all of applied mathematics.
Yeah.
We need to explore the central limit theorem.
Here's where it gets really interesting. And remember the promise we made at the start. Pure intuition, no dense math, no intimidating Greek letters on a whiteboard. We are going to rely on a thought experiment to internalize this concept.
Okay, let's hear it.
Let's imagine we possess a device that allows us to pause and rewind time. We run our 1,000 user green button experiment on our perfectly representative sample, and we calculate a 12% conversion rate. That 12% is our sample mean, the average behavior of that specific group.
Right.
Now imagine we hit the rewind button, we reset the timeline, we grab a completely different random sample of 1,000 representative users, and we run the exact same test again under identical conditions. This time, because humans are unpredictable, the conversion rate comes back at 11.8%. We rewind again, different 1,000 users. This time it's 12.1%.
The crucial observation here is the variance. Every single time you repeat the experiment, your sample mean will shift slightly. You're selecting different individuals with different moods, different bank balances, and different attention spans. Human behavior is inherently noisy. The underlying data generation process is messy. You will almost never calculate precisely 12,000% twice in a row.
So imagine we automate this time machine. We write a script that pulls 10,000 distinct random samples of 1,000 users each, and for every single sample, it logs the conversion rate. We end up with a massive spreadsheet containing 10,000 different averages. 12.0%, 11.8, 12.1, 11.5, 12.5, 11.9. If you look at that raw column of numbers, it just looks like chaotic, random noise. It looks like the static on an old television.
But then you visualize it. You take those 10,000 separate averages and you plot them on a histogram. You stack them up to see the frequency of each result.
Yeah.
And that is where the mathematical magic reveals itself. Even if the underlying raw behavior of individual humans is completely erratic, nonlinear, and unpredictable, when you take the averages of those many samples, those averages will naturally, inevitably, and flawlessly organize themselves into a beautiful, perfectly symmetrical shape.
Yeah.
They form a predictable bell curve. This is what statisticians call a normal distribution.
It's like discovering a hidden fundamental law of order operating quietly underneath all the chaos of the universe. No matter how messy the individual clicks are, the averages magnetically pull together in the center, creating this smooth, elegant bell shape. Most of the averages cluster tightly around the middle, with fewer and fewer landing out on the extreme tails. Why does understanding this specific shape matter so profoundly for a developer who is just trying to train a predictive model?
It matters because the central limit theorem provides the bridge from the known to the unknown. You do not need to memorize the complex integral calculus behind the theorem. What you absolutely must internalize to be industry-ready is the pure intuition averages stabilize. Because we know for a mathematical fact that sample averages will always form that specific predictable bell curve, we understand exactly how they behave geometrically.
We know the shape.
We know the shape. We know that the vast majority of our samples will land right in the fat, dense middle of that curve, incredibly close to the true, unobservable reality of the entire population. Only a very small fraction of highly unusual samples will land way out on the skinny, tapering edges.
So, because we understand the architectural shape that these averages inevitably form, we can mathematically calculate the probability of our position. If we run one test and get 12%, we can calculate how likely it is that our 12% is sitting right near the true center of the universe, or if we accidentally grabbed one of those weird, rare outlier samples on the extreme edge.
Exactly. When we map this to industry ML applications, this theorem is the secret engine powering everything we trust. Think of a deep learning engineer training a massive network. They don't pass the entire data set through the network at once. They use mini batches.
Right, batch processing.
They pass small samples of data, calculate the error, the average loss, and update the model. The only reason stochastic gradient descent, the algorithm that trains almost all modern AI, actually converges to a solution instead of bouncing around randomly, is because of the central limit theorem. The average gradients stabilize.
That is an incredible connection. The very mechanics of how a neural network learns to recognize a face or generate text rely on the fact that the average of a sample points toward the truth of the population.
It is the bedrock of estimating uncertainty. When you are asked to estimate how well your new model will perform in the real world next quarter, you cannot predict the future. But you can rely on the central limit theorem to guarantee that your cross-validation test results are stable indicators and not just random fluctuations. It allows us to quantify our own ignorance.
Averages stabilize. That is such a powerful, calming mental model to carry forward. It removes the panic of staring at a single, messy log file. It promises that if you aggregate enough information correctly, the underlying truth will start to reveal its structure. Which leads us perfectly into the practical, day-to-day application of this idea. How do we communicate that stability to the business side? We need to translate this bell curve into a business decision. And that brings us to confidence intervals.
The central limit theorem provides the theoretical physics of our universe, but confidence intervals provide the practical engineering tool we use in the boardroom.
Let's bring it back to the engineer standing in front of the CEO's dashboard. You ran the A/B test, you got a 12% conversion rate for the new green button. An amateur, someone who doesn't understand inference, might burst into the office and confidently declare, the new conversion rate is exactly 12.0%. But a senior industry professional, someone who understands the variance we just discussed, would never, ever say that. They know that 12% is just 1 point from one sample on one day.
The professional understands that the single number, what we call a point estimate, is almost certainly wrong. It is mathematically improbable that your sample mean perfectly matches the population mean down to the 10th decimal place.
Instead, the professional says, based on our data and the variance observed, the true conversion rate of the green button for our entire global user base is between 11% and 13%, with 95% confidence.
That shift in communication is monumental. You are transitioning from a fragile, easily disproven absolute to a robust, mathematically defensible range.
To make this incredibly intuitive, think of it like this. Imagine you are standing on the shore of a muddy, opaque lake, trying to catch a specific, invisible fish. That fish represents the true, unobservable conversion rate of the entire infinite population.
I like this.
Now, at declaring to the CEO the rate is exactly 12% is like throwing a single, sharply pointed spear blindly into the muddy water, hoping to impale that specific fish dead center. If your aim is off by even a millimeter, or if the fish moves slightly, you miss entirely. You are demonstrably wrong.
And because of the natural variance we established with the time machine thought experiment, because every sample is slightly different, your spear will almost always miss the exact true value.
But a confidence interval, that is entirely different. That is like taking a wide, heavy fishing net and throwing it out over the water. You aren't trying to hit a single microscopic point. You are throwing a net that covers an entire area of the lake, and you are saying, I cannot see the fish, but based on the ripples in the water, I am highly confident that the true value is currently trapped somewhere inside the boundaries of this net. The interval, stretching from 11% to 13%, is the physical width of your net.
That analogy perfectly captures the mechanics. In plain meaning, a confidence interval is simply a range of values constructed around your sample mean where the true population value is highly likely to exist.
But hold on, what does the 95% confidence part actually mean? Does it mean there is a 95% chance the fish is in that specific net I just threw?
That is a very common misconception. The 95% refers to the reliability of your net throwing process, not the specific net you just threw. It means that if we repeated this whole A/B testing process 100 times, if we pulled 100 different samples and threw 100 different nets based on those samples, we expect that 95 of those nets would successfully capture the true invisible fish, and 5 of the nets would land in the wrong spot entirely and miss it.
I'm looking at the notes on how we actually construct this in Python. When an engineer uses a library like SciPy to calculate this interval, the width of the net isn't arbitrary. It's dictated by two things: the size of your sample and the variance or messiness of your data. If you only test 10 people, your data is incredibly unstable, so the math forces you to throw a massive, incredibly wide net to maintain that 95% confidence. You might have to say the conversion rate is between 2% and 22%.
This raises an important question regarding practical utility. A net that wide is technically accurate, but is it useful? If you go to a CEO and say, the new model will generate between $0 and $50 million,
Yeah.
you haven't helped them make a decision.
But if you increase your sample size, if you test 100,000 users, the central limit theorem tells us the averages stabilize significantly. The data becomes less noisy. And because the math recognizes that stability, it allows you to shrink the net. You can confidently say the rate is between 11.9% and 12.1%.
Which is a highly actionable insight. If we map this directly to industry ML applications, confidence intervals are the primary tools we use for risk analysis. Let's say you have designed an ML model to automate the detection of fraudulent credit card transactions. Your offline validation tests give you a point, Steph. Estimate this model reduces fraud losses by $1 million a month.
But wait, if the lower bound of your confidence interval is only $100,000 and the new cloud compute infrastructure required to run this massive neural network costs $500,000 a month, isn't there a severe risk the CEO just scraps the project entirely? How does the ML engineer argue for deployment when the interval is that wide and potentially negative for ROI?
That is exactly the conversation that should happen. The ML engineer doesn't hide the risk. They expose it mathematically. If the net is too wide and crosses into negative ROI, the engineer's recommendation shouldn't be to deploy. It should be, we need to run a larger experiment to shrink the interval and reduce the uncertainty before we commit infrastructure budget. Confidence intervals give stakeholders the actual context required to make million-dollar decisions. They prevent engineering teams from overpromising based on a single lucky validation score and under-delivering in production.
So what does this all mean? We've covered the net we throw to capture reality. We know how to communicate uncertainty. But eventually, the analysis phase has to end. We have to make a final binary decision. Do we deploy the green button to the global population, or do we delete the branch and stick with the blue button? Do we deploy Model B or stick with Model A? We have our confidence interval, but we still need a definitive mechanism to prove that the 2% jump we observed isn't just a statistical phantom. We need to put our data on trial, and that is where we enter the realm of hypothesis testing.
Hypothesis testing is the formal, rigorous scientific process of checking whether the difference we observed in our sample is likely a real structural change in the underlying universe or just the natural chaotic noise of the system.
Let's set up the courtroom. In hypothesis testing, we always start by defining two opposing narratives. On one side, we have what is called the null hypothesis. I always visualize the null hypothesis as the ultimate cynic sitting in the back of the room.
The cynic. I like that.
The null hypothesis looks at your shiny new 12% conversion rate and says, there's nothing special happening here. Your green button does absolutely nothing to human psychology. The difference between the 10% baseline and your 12% result is pure random luck. You just happen to sample a bunch of people who are going to buy anyway. It's just noise.
It is the assumption of the status quo. In an ML context, it assumes zero effect, zero difference, zero algorithmic improvement. It is the baseline reality we assume is true until proven otherwise.
Right. And on the other side of the courtroom, we have the alternative hypothesis. This is what you, the engineer who spent 3 weeks building Model B or designing the green button, actually want to prove. The alternative hypothesis says the green button genuinely changes behavior. Model B is structurally superior at finding patterns. The difference we see in the sample reflects a real difference in the unobservable population. Hypothesis testing is essentially a battle to the death between these two ideas based on the evidence collected.
And remember, the foundational rule of most justice systems, innocent until proven guilty. In the realm of statistics, the null hypothesis, the cynic, is presumed entirely true. You have to gather enough overwhelming statistical evidence from your sample to defeat the cynic, to forcibly reject the null hypothesis.
I was looking at the notes on error types, and this is where it gets really stressful for the engineer making the deployment call, because the judge in this courtroom isn't perfect. We can make two massive mistakes.
Yes, type I and type 2 errors. They are the nightmare scenarios of hypothesis testing.
Let's break those down. A type I error, or a false positive, is when the cynic was actually, the green button really does nothing, but our data was so weird and lucky that it tricked us. We reject the null hypothesis incorrectly. We throw a launch party. We spend weeks refactoring the global code base to deploy the green button or Model B. We spin up new servers. And it's completely useless. It costs the company hundreds of thousands of dollars in engineering hours for zero benefit.
Exactly. A type I error is a failure of over-eagerness. You bleed a mirage. The other side of the coin is the type 2 error, or false negative. This is when the alternative hypothesis was true. Your new deep learning model genuinely is a massive breakthrough that could increase company revenue by 20%, but your sample was unusually noisy or too small to prove it. The evidence wasn't strong enough to defeat the cynic, so you failed to reject the null hypothesis.
And what's the consequence of that? You take this brilliant revolutionary model, you assume it's garbage, and you throw it in the trash. You leave millions of dollars on the table because your test couldn't detect the signal.
The entire design of a hypothesis test setting, sample sizes, choosing significance levels is an exercise in balancing the risk of these two errors. You want to be sensitive enough to detect real improvements to avoid type 2, but rigorous enough to block statistical mirages from reaching production to avoid type I.
If we map this to our daily lives as ML engineers, hypothesis testing isn't just for UI changes. It's how we do fundamental model comparison. When you have Model A and Model B from our intro, you don't just look at which one has a higher F1 score on the validation set. A 0.01 difference in an F1 score could easily be noise. You run a hypothesis test on their performance metrics to prove that Model B is statistically significantly better than Model A.
It is also the core logic behind feature selection. Remember the problem of deciding whether to include that expensive new session duration variable in your dataset. You formulate a null hypothesis that says this new feature has absolutely zero predictive power. You then train your model with and without the feature and measure the difference in loss. If the improvement is strong enough to reject the null, you justify the computational cost and keep the feature. If not, you aggressively prune it out to save complexity.
So we've set up the trial. We understand the risks. The cynic says it's luck. The engineer says it's a real signal. But the judge overseeing this trial cannot make a ruling based on feelings or visual charts. The judge needs a hard, standardized metric, a specific numerical value to make the final objective ruling. And that brings us to the most famous, most dreaded, most published, and most heavily debated metric in all of modern science. We need to demystify the p-value.
What's fascinating here is how universally utilized the p-value is across every scientific discipline, from quantum physics to pharmaceutical trials to AI engineering, and yet how widely misunderstood it is, even among seasoned tech professionals.
Let's break it down to its absolute bare metal conceptual form. We are back at the e-commerce test. We saw a 2% improvement with the green button. The ultimate question the p-value is designed to answer is this. If the cynic is right, if we assume as an absolute fact that the green button truly has zero effect on human psychology, how likely is it that we would randomly observe a 2% improvement in our sample of 1,000 users by pure, dumb statistical chance?
The phrasing of that premise is the most critical part. The mathematical calculation of the p-value assumes, without question, the null hypothesis is true. It assumes you are living in a universe where the button color doesn't matter. It then calculates how weird, extreme, or surprising your observed data is within that specific boring universe.
So let's say we plug our numbers into a Python statistics library, we run the function, and it spits out a p-value for our button test of 0.03 or 3%. What is that telling the engineer?
It provides a very clear probability. If the null hypothesis is true, you would only expect to see a 2% jump in your data 3 times out of 100 tests. That is a highly unlikely event. It means your data is very surprising. Because it is so rare to see this result in a world where the button does nothing, a rational person concludes that they probably don't live in a world where the button does nothing. The evidence forces you to reject the cynic's view. You reject the null hypothesis.
A small p-value, typically anything under the industry standard threshold of 0.05 or 5%, means the data is highly incompatible with the idea of pure luck. It gives you the mathematical clearance to say, the evidence is too strong, this improvement is likely real, let's deploy Model B. But what if the script returns a p-value of 0.40 or 40%?
A large p-value entirely changes the narrative. It means that if the green button did absolutely nothing, you would see this exact 2% jump 40 times out of 100 just by randomly shuffling users around. It means your result is not special, surprising, or extreme at all. It is perfectly normal statistical noise. In that case, you fail to reject the null hypothesis. You assume the button color doesn't matter, and you don't bother deploying the complex code change.
Okay, we've defined what the p-value is, but I am looking at the notes regarding how often this metric is abused, and I know you want to give a stern warning to the listener right now, because there is a trap here that catches so many junior developers and even product managers. What is the p-value, not d?
This point is paramount. Please, if you are listening to this, burn this into your mental model of statistics. The p-value is not the probability that your hypothesis is true. I will repeat that because it is the most common error in data science. It is not the probability that your alternative hypothesis is correct. It is not a score of how right your new model is.
I want to really expand on that because that linguistic trap is so easy to fall into. A product manager sees a dashboard indicating a p-value of 0.01 for the new recommendation engine. Their immediate intuitive reaction is to think, awesome. There is a 99% chance my new engine is superior. It has a 99% probability of being the right choice.
And that conclusion is mathematically fundamentally false. The p-value only tells you about the data, assuming the null is true. It calculates the probability of seeing your data, given the null hypothesis. It does not, and mathematically cannot tell you the probability of the hypothesis, given the data.
It seems like a subtle linguistic trick. Probability of data given hypothesis versus probability of hypothesis given data. But mixing them up leads to terrible science.
It leads to catastrophic engineering. The p-value simply measures how surprised we should be by our data if the status quo are true. It is a measure of surprise.
A measure of surprise. I love that framing. A small p-value means the data is very surprising if the cynic is right. So we stop believing the cynic. But wait, I'm looking at the notes on something called p-hacking or data dredging. If the p-value is just a measure of surprise, can't an engineer just manipulate the system to find surprising things?
That is the dark side of statistical inference. Let's say you are determined to prove that your new feature engineering pipeline works. You test 100 different, completely random, useless variables against your target metric. Because a p-value of 0.05 means a 5% chance of seeing a result by pure luck, testing 100 useless variables guarantees that, on average, 5 of them will show a statistically significant p-value under 0.05 purely by accident.
So if you only publish a report on those 5 lucky variables and hide the 95 failures, you look like a genius who found massive signal when in reality you just mined the noise until you found a statistical anomaly.
Exactly. That is p-hacking. It is why modern ML pipelines employ rigorous defenses against it. We use techniques like Bonferroni corrections to adjust the threshold when running multiple tests, or we utilize strictly quarantined holdout datasets. You might find a p-value of 0.01 on your validation set, but if it doesn't hold up on the unseen test set, we assume it was a dredged anomaly. The p-value is a powerful tool, but it requires an ethical, disciplined operator to prevent it from becoming a weapon of confirmation bias.
That distinction between statistical significance and practical reality is crucial. A massive sample size can make a tiny 0.001% improvement statistically significant, generating a tiny p-value. But a 0.001% improvement doesn't justify refactoring a million lines of code. It might be statistically significant, but it lacks business significance.
Precisely. The p-value tells you if the effect exists. It does not tell you if the effect matters.
So we have the ultimate gatekeeper metric. We understand the trial. Now we need to talk about the different kinds of data we might actually put on trial. Because not all datasets look the same, and the specific Python functions we call depend heavily on the shape of our numbers. That brings us to comparing the two fundamental types of data, comparing means versus comparing proportions.
While the overarching logic of hypothesis, testing null versus alternative, generating a p-value remains identical, the specific mathematical distributions and formulas we use change entirely depending on the nature of the data we are observing.
Let's contrast two completely different industry scenarios from our research. Scenario A. You work for a real estate platform like Zillow. You are tasked with building a model to predict average house prices in two rapidly changing neighborhoods to see if one is significantly outpacing the other. Scenario B is our classic e-commerce website comparing the percentage of users who click the new checkout button versus the old one.
These two scenarios perfectly represent the two massive foundational branches of data types you will encounter in any engineering role. Predicting house prices involves continuous numerical data. A house price can be any value across a massive spectrum. When you analyze this, you are comparing averages. In statistics, we call this process comparing means. You are mathematically asking, is the mean house price in neighborhood A statistically different from the mean house price in neighborhood B?
Because a house can cost $300,000 or $300,050. It exists on a fluid, continuous scale. You calculate the variance of those continuous numbers. But with the website clicks in scenario B, a user cannot half-click a button. They either click it or they don't. It's a binary 0 or 1, yes or no event.
And because it is binary, categorical data, the concept of a mean changes. You aren't looking at a continuous average, you are looking at percentages or fractions of the whole. In statistics, we refer to this as comparing proportions. You are asking, is the proportion of clickers in the green group statistically different from the proportion of clickers in the blue group?
Both scenarios require rigorous hypothesis tests to prove the observed difference isn't just luck. But the nature of the data dictates the approach. For means, you might use something like a student's t-test. For proportions, you might use a chi-square test or a z-test for proportions. And this mathematical division maps flawlessly to the very architecture of machine learning algorithms.
If we connect this to the bigger picture of AI design, this distinction is the exact dividing line between the two main types of supervised machine learning: regression and classification. When you are predicting a continuous number like the house price or the temperature tomorrow or the exact lifetime value of a customer in dollars, you are building a regression model. Evaluating the performance of a regression model involves metrics fundamentally based on analyzing means, like mean squared error or mean absolute error.
You are measuring the average distance between your prediction and reality. And conversely, when you are predicting a category like whether an incoming email is spam or not spam, or whether a tumor in an image is benign or malignant, or whether a user clicks or doesn't click, you are building a classification model. Evaluating a classification model involves metrics based on proportions of correct guesses, like accuracy, precision recall, and the F1 score.
Means map directly to regression. Proportions map directly to classification. These are the two foundational pillars of ML model architecture. Knowing which type of data you have in your database tells you which statistical test to run during exploration, which in turn tells you which class of ML algorithm to deploy for production.
It all connects so beautifully. The statistics dictate the geometry of the model. Okay, we have covered a massive, sprawling amount of ground today. We've journeyed from the vast, unknowable, infinite population down to the flawed, biased samples we actually work with. We've visualized the stabilizing magic of the central limit theorem. We've thrown the heavy fishing net of confidence intervals over our uncertainty, and we've put our data on trial with hypothesis testing to defeat the cynic using the p-value. Now it's time to bring all of these abstract concepts together. Let's do a final synthesis, building the comprehensive big mental model.
To truly solidify this mental model for the listener, let's connect today's deep dive back to the broader curriculum. Think back to Lecture 1 in this series, where we extensively explored descriptive statistics. Descriptive stats, calculating the mean, finding the median, measuring the standard deviation, their entire purpose is simply to tell us what the data sitting right in front of us looks like. They describe the physical characteristics of the sample.
Right. If descriptive stats are like a photograph, they just show you exactly what was in the room at the moment the shutter clicked.
But today, Lecture 2 is an entirely different beast. Today is about inferential statistics. Inferential stats take that photograph, look at the specific details and differences within it, and tell us whether we can trust those details when we apply them to the wider unseen universe outside the room. Machine learning, at its absolute core, is an industry utterly obsessed with comparisons.
We are constantly, obsessively comparing. Is Model A better than Model B? Does the data set with a new feature outperform the baseline data set? Does version 1 of the app generate more revenue than version 2?
And here is the brutal truth that separates junior coders from senior architects. Without statistical inference, you simply cannot validate any of those comparisons. Without inference, you are just a person staring at two numbers on a screen and making a gut guess. Inference provides the rigorous, mathematical, professional framework required to definitively say, yes, this change matters. It is the shield that protects your codebase from illusions.
To really hammer this home and make sure you are industry ready, we are going to do a translation drill. This is an interactive role-play exercise to prep you for the real world of corporate data science. I'm going to play the role of a very senior, intimidating, jargon-heavy machine learning engineer presenting findings in a high-stakes board meeting. My colleague here will act as the universal translator, breaking down my dense jargon into the clear, intuitive mental models we've built today. Ready?
I am ready. Let's decode the industry speak.
All right, I step up to the projector. Looking at the recent multivariate A/B test results for the new deep learning recommendation algorithm, we have run the analysis and can confirm that the positive delta in user engagement metrics is statistically significant.
Translation for the learner. We defeated the cynic. It is highly unlikely that the jump in user engagement was just random chance or a lucky sample. We have mathematical confidence that the new deep learning algorithm actually caused a real change in user behavior, and it is safe to trust the improvement.
Next slide. However, before we initiate a global rollout across all regions, we must acknowledge a critical risk factor. The demographic distribution of our training sample indicates it may not be representative of our emerging European user base.
Translation. We are worried about sampling bias. Our dataset might be heavily skewed. We likely trained and tested this model exclusively on North American users. If we blindly deploy it to Europe, the model might suffer a catastrophic generalization failure because it learned a behavioral reality that simply doesn't exist over there. The keyhole was pointed at the wrong part of the room.
Excellent. Next bullet point on the agenda. When we ran the two-sample t-test on the regression model predicting next quarter ad spend, we noted that the 95% confidence intervals for Model A and Model B severely overlap.
Translation. The mathematical fishing nets we threw to capture the true, real-world performance of both models landed right on top of each other in the lake. Because the nets overlap, the true value for Model A could easily be identical to the true value for Model B. This means the difference between these two models is not reliable. We cannot confidently say one is definitively better than the other. They are likely performing identically in reality, despite what the slight difference in their raw validation scores suggests.
All right, last one. We evaluated the impact of integrating the new NLP sentiment analysis embedding, and the p-value for the performance increase came back at 0.01.
Translation. If the new sentiment feature truly had absolutely zero impact on our model's accuracy, we would expect to see a performance jump of this size only 1% at the time by pure random luck. Because a 1% chance is incredibly rare and surprising, we reject the idea that it's just statistical noise. The feature clearly contains strong predictive signal, it is highly relevant, and the computational cost to include it is mathematically justified.
That drill is so incredibly powerful. It proves that all this intimidating mathematical terminology, p-values, statistical significance, representative samples, is really just an academic way of describing basic intuitive human concepts of trust, uncertainty, and logic. Which brings us to our final provocative thought for you to mull over as we wrap up this massive deep dive. We've spent a lot of time talking about how machine learning predicts things, house prices, clicks, fraud. But the paradigm-shifting realization you must walk away with today is that modern machine learning doesn't just predict.
No, it doesn't just passively observe. Machine learning actively experiments. It dynamically probes reality. Reinforcement learning agents constantly compare variations of reality against each other. And crucially, a mature ML system must validate its own findings mathematically.
And without statistical inference, every single improvement your complex Python code produces could be a complete illusion. You could spend 6 agonizing months optimizing a massive neural network, tuning hyperparameters, see the validation accuracy score tick up by a single percentage point, and throw a massive launch party only to deploy it and find out it was entirely statistical noise. You must use the tools of inference to trust your improvements, to detect the chaos of randomness, and to avoid those embarrassing, career-damaging false conclusions. Inference isn't just a math requirement, it is the ultimate defense mechanism for your code.
That is the perfect way to conceptualize it. It grounds the abstract theories of probability directly into the daily high-stakes reality of software engineering.
So let's explicitly bridge today's topic to what's coming next in your journey. So far in this series, we've covered how data varies in Lecture 1, focusing on the snapshot of descriptive stats. Today, we've conquered how data infers in Lecture 2, stripping away the fear from hypothesis testing, biased samples, and the p-value. Next time, we are making a massive conceptual leap. We are moving away from probability and statistics entirely and stepping into the visual world of geometry to explore how data lives in space. We will uncover the hidden geometric language of machine learning, where raw data sets become multidimensional shapes and complex algorithms become simple navigational tools moving through vector space. It is going to fundamentally change how you see data.
It is a phenomenal shift in perspective. Moving from calculating probabilities to visualizing dimensions makes the black box of AI incredibly transparent. I cannot wait to explore that framework.
Before we go, we have a mandatory challenge for you, the listener. We actually skipped one crucial translation during our drill, and we want you to test your newly built mental model right now. Head down to the comments section and translate this piece of expert jargon based purely on the intuition you learned today. Here's the phrase. The p-value is 0.01. Don't use mathematical formulas, don't copy textbook definitions. Write your own plain English translation explaining what that actually means for an engineer making a decision. Put it in the comments below.
Explain it as if you were talking to a friend over coffee or pitching a CEO. That ability to translate math to business logic is the true mark of an industry-ready professional.
And if you want to keep building your industry-ready AI mindset, make sure to like this deep dive, share it with a fellow coder who might be terrified of statistics, and subscribe to 60 Seconds Academy. Drop any questions you have about populations, samples, or confidence intervals in the comments, and we'll see you in the next deep dive.